So in chapter 12, we were calculating for Q, or the quotient product values, in which we were using them, comparing them with the value of the equilibrium constant K to determine to what direction the reaction is leaning to achieve equilibrium. Okay, since Ksp, or solubility product constant, is also an equilibrium expression for a saturated solution, that is, we can predict whether precipitation will occur or whether more solid will dissolve, given a value of Q, which for this case we're gonna call it Qsp. Okay, so basically all of these concepts are actually the exact same as we have discussed for K and Q in chapter 12. So let's say, for example, if Qsp is equal to Ksp, then you have a saturated solution, meaning this system is in equilibrium. The rate of dissolution is equal to the rate of precipitation or crystallization. Okay, if the value of Q is large, then that means that the reaction shifts heavily to the left, okay, which just means that precipitation happens, okay, and precipitation will not stop until you reduce ion concentrations, and that will lead to Qsp being equal finally to Ksp. And then the opposite is true. When Qsp is smaller than Ksp, then you have an unsaturated solution, so the solid continues to dissolve, and it will continue to dissolve until Qsp is greater than, or is equal to rather, than Ksp. Okay, let's work on one problem, but again, for Qsp, you're just like using initial concentrations, okay? That's how different it is from Ksp. So this problem, let's see whether this system is a saturated solution or not. It's asking whether the system has reached equilibrium. Okay, so here we just set up an expression for Qsp, and similar to Q, the expression for Qsp should also be the same as Ksp. Okay, so the Qsp here should be concentration of silver that we're given and concentration of chloride. Okay, they're both equal to each other, so we can just say that that is equal to 1.2 times 10 to the negative 5 molar, okay, squared, and this is just equal to 1.4 times 10 to the negative 10, okay. And as you can see here, this value of Qsp, I just added this information, by the way. This value of Qsp is actually much less than Ksp. Okay, so the answer to the next question is, will more silver chloride dissolve? That will be yes. And that will happen until Qsp is equal to Ksp. Okay, let's answer the next problem. So here you're mixing barium nitrate and sodium carbonate. It is a precipitation reaction, as we have seen in chapter 6 before when we were doing 105. And the first question asks you, will a precipitate form? And if so, what is the mass? Okay, so in this question, the first question actually just asks you, based on a Qsp value, will there be any precipitation? So you want to calculate first the concentrations of barium and carbonate in solution. I mean, if they do form a saturated solution. Okay, so the species here again in consideration should be barium carbonate, which is formed from barium ions and carbonate ions, as per the net ionic equation. Now keep in mind that when you mix these when you mix the nitrate of barium and sodium carbonate, they actually have different volumes. So when you add these two together, there will be a new volume and there will be a new molarity. So let's calculate first the concentration of barium and carbonate in solution when they are mixed together. Okay, so in a solution, okay, in a mixed solution, and again, prior to precipitation, if it's gonna happen, if it happens, just a disclaimer, we don't know that yet. Okay, so the concentration of barium ions should therefore be, we're just going to use the formula for molarity. Okay, so here the number of moles is equal to 0.10 molar. Okay, that's how much, that's the original concentration of barium nitrate. Okay, times 20.0. This is basically M1V1, by the way. And that's divided by 70.0 ml. Okay, I don't need to convert because those will just cancel out. I'm gonna get 0.029 molar. Okay, and then after that, the concentration of carbonate should just be 0.10 molar. Okay, times 50.0 ml divided by the total volume, which is 70.0 ml, and that should just give you 0.071 molar. All right, and then from there, since you now have concentrations of barium and carbonate in solution, we can calculate for Ksp. Okay, again, the expression for Ksp is just the same for Ksp, and for barium carbonate, Ksp should therefore be the concentration of barium 2 plus in solution times the concentration of carbonate in solution. Okay, and we just multiply the values that we have just calculated earlier. So that's going to be 0.029. Let's just ignore the units because this is a Q value anyway, times 0.071. And this should just give you 2.1 times 10 to the negative 3. Okay, and remember that the Ksp for barium carbonate is actually 8.1 times 10 to the negative 9. So this is actually higher than Ksp. So therefore, yes, precipitation will occur or will form to dissolution. So if that happens, the next thing that you want to know is to figure out how much of that precipitate will be produced. So you just need to write an ICF table, okay? Or if you don't want to write an ICE table, or an ICF table rather, not an ICE table, you can also do limiting reagents. Okay, so the net ionic equation for the formation of barium carbonate is as follows. Okay, and we actually have the following number of moles. Okay, so we have here for barium nitrate 20 times 0.1. So the amount of moles of barium there should be ICF. So this should be 20.0 ml times 0.10. Okay, here we're not considering again the molarity because this is just an ICF table. Okay, so that will be equal to 2.0. Okay, and then for the number of millimoles of carbonate, that will be 50.0 ml times 0.100 molar. Okay, is equal to 5.0, and we begin with no barium carbonate. Okay, there should be minus 2. Okay, the limiting reagent therefore is barium carbonate. Okay, this should be plus 2. Okay, so that at the end we get nothing of barium carbonate, we have something of carbonate. Okay, we are left over with 3. That has some ramifications, we will discuss that later, and we will end up with 2 millimoles of barium carbonate. So to determine how much mass of barium carbonate will form, so we just use this number of millimoles, convert that into moles. Okay, so that will be 2.0 millimoles. And since that's the prefix milli, you know that for every 1000 millimoles, similar to milligram and milliliter basically, you have a mole. Okay, and then using the molar mass of barium carbonate, we can determine the mass of how much barium carbonate we have. So that's 1 mole of barium carbonate, and the molar mass is 197.34 grams of barium carbonate, and that should be equal to 0.39 grams of barium carbonate. That's how much the precipitate weighs. Okay, the next question is calculate the concentrations of barium and carbonate at equilibrium with a solid carbonate. Okay, remember when I actually said that there will be some ramifications as to the presence of this carbonate. Okay, so what this actually means is remember that this is actually not really zero, the millimoles of barium. So even some solid has indeed precipitated out 0.39, but there will be a tiny amount of barium 2 plus and carbonate ions in solution, okay, which will be at a dissolution and precipitation equilibrium. But we cannot ignore now that after this precipitation we have an excess of carbonate ions. So basically what I'm trying to say here is we're going to write an ice table, okay, to determine the concentrations of barium and carbonate in equilibrium practically, and then from there keeping in mind that we have some amount of carbonate. Okay, so this one should be molarity, and then barium carbonate, okay, and that should be equal to barium 2 plus CO3 2 minus. Okay, so here we have to consider molarity, so this one's ignore. As we have seen from the previous ICF table, this one's 0. Okay, now for the concentration here of carbonate, we're just going to use how much left over we have, 3.00 or 3.0 rather millimoles, and then divided by the total volume of the solution is 70.0 ml, and we have at the very beginning 0.043 molar of carbonate. That's how much is in excess in solution. Okay, and then this will be plus S. So at equilibrium this will just be S, and then this will be 0.043 plus S, but that S value must be very small, so we can just assume that this is equal to 0.043. Okay, and then from there we can use the Ksp value of barium carbonate to calculate for S. So we set up next a Ksp expression, so that's 8.1 times 10 to the negative 9 is equal to S times 0.043. Okay, so therefore S should be equal to 1.9 times 10 to the negative 7, okay, molar. Okay, that will be the value of barium as well in solution. Okay, so again, even though we did say it was 0 here, I mean, we know that there are some amounts of barium in equilibrium, at equilibrium rather, in precipitation and dissolution, and that's basically this value. Okay, and then the amount of carbonate ions will just be 0.043. Okay, you can add this number, but it's gonna be negligible anyway, so that's carbonate ions is equal to 0.043. Okay, and then the last question is what would be the minimum amount of barium ions in solution to initiate precipitation? So for this one, we're just going to assume that we begin with how much concentration of carbonate we have, which is this value. Okay, and then from there, if you have that amount of carbonate, how much is the bare minimum to actually initiate the reaction? Remember that currently the situation is that barium carbonate, or the carbonate rather from sodium carbonate, is actually in excess in solution. So we can just set up an ice table to illustrate what I'm saying. So that will be barium carbonate going to barium 2 plus carbonate ions. Okay, and then again we're going to write an ice table. Okay, and then we're gonna begin here with 0, and then for carbonate we're gonna start with 0.071. Okay, note that, by the way, in using this number 0.071, we're shooting for a solution, for a total volume of the solution to be equal to 70. Okay, so we're still working here at the 70 ml solution total. Okay, so this one will be plus S at equilibrium plus S. This will be S. This will be 0.071 plus S. Okay, and then we can assume that this is just 0.071. Okay, so therefore this will be set up the Ksp expression 8.1 times 10 to the negative 9 is equal to S times 0.071 molar, and S, which is equal to the concentration of barium needed minimally, or the minimal amount rather of barium needed if you have that amount of carbonate, should be 1.1 times 10 to the negative 7 molar. Okay.